Okay, we have created a function which calculates the weight of evidence. However, we still don't know how to interpret this measure. The easiest way to evaluate the weight of evidence is to visualize it. To create charts, we need to import the matplotlib library. We'll only need the pyplot module, so let's import matplotlib.pyplot as PLT. We're going to create the charts with matplotlib, but to make them prettier, we can use another library called Seaborn. So let's import Seaborn as SNS. To override the default matplotlib look, we use sns.set. You can think of Seaborn here as a nice skin for matplotlib. Okay, we have all the libraries we need to create visualizations. Since we will create these plots for all discrete variables, this time we will directly write a function that visualizes the data. Again, we use the def statement to do this. Let's name it plot by weight of evidence. The function will take the results from our calculations contained in the weight of evidence data frame we created. So the first argument of the function will be a data frame, which we'll call df_wo. Actually, the data frame with the results contains all the information we want to visualize, so this is really the only argument we need to pass to the function. What we want to visualize are the categories of the independent variable on the x-axis and the weight of evidence on the y-axis. Both of them are contained in the data frame with the results. However, there are other things on the charts we may want to customize. Our charts for different variables should be uniform, and I can hardly think of anything special to distinguish between variables. Well, maybe there is one thing. We said we want to visualize the categories of the independent variable on the x-axis. For the grade variable, the names or the labels of the categories consist of single letters, from A to G, and there are only 7 of them. But for some other variables, the names may be very long. Besides, there may be hundreds of categories. In such cases, the independent variable category labels overlap below the x-axis and we can't read them. What we can do is rotate them in a suitable way, so they could be displayed better. So this is the second parameter we can add to our function. Let's do this by indicating how many degrees it should rotate the labels of the x-axis variable compared to displaying them horizontally, which is 0 degrees. Let's name the parameter rotation of x-axis labels. Later in the function, when we plot the data, we will set the labels of the x-axis to be rotated with the number of degrees contained in the rotation of x-axis labels variable. For now, you have to trust me on that. We will rotate the labels only when necessary, so it will take some time before we see this argument in action. Since we won't be using it every time, we should set some default value. In this way, if we omit the parameter, the function will use its default value. By default, the label should be displayed horizontally, so let's set it to 0. Okay, now we have to write the actual function. We wanted to plot the categories of the independent variable on the x-axis and the corresponding weights of evidence on the y-axis. To make it clear, let's assign values to 2 variables named x and y. The categories of the independent variable are contained in the first column of the data frame with results, so from the data frame df_wo, we select the column with index 0. That would be enough if all the independent variables were text strings or another suitable data type. Remember that the values of the independent variable must be displayed as labels on the x-axis, so they must be of data type easily recognizable to display. We know the grade variable of string type, but we can't be sure about the others. So just in case, let's turn the values into strings. We do that with the applyString method. Alright, so far we turned the contents of the first column into strings. While working on this case, I found that matplotlib did not fare well with data frames and strings, but performed perfectly well with ND arrays. One of the reasons is that it is optimized to work with NumPy and SciPy. To prevent any issues, let's turn the results of this expression into an array with the NumPy array method. Okay, and that's it. Now we can be certain that whatever data type the independent variable is, its labels will almost always be turned into text strings ordered in an ND array that will always be suitable for plotting. Good. Now it's time for the Y variable. It is the weight of evidence, so we take the column named WOE from the data frame. It's always a numeric variable, and we don't have to do anything special about it. X and Y contain everything we want to plot on the X and the Y axis. This by itself is enough to plot the data. However, to make the charts easy to interpret, I'll apply some formatting. First, let's specify the dimensions of the chart. We do that with the plt.figure command. In round brackets, we set the parameter fig size to bracket 18, 6 bracket. The two numbers specify the width and the height of the chart, respectively, in inches. So we'll get a chart that is 18 by 6 inches. I found those dimensions to work very well for me. Next, let's plot the data. The command to do that is plt plot. We specify the arguments in round brackets. We plot X and Y, and that's it. This statement alone will plot the categories of the independent variable on the x-axis, and for each of them, its weight of evidence. As you can probably imagine, the chart won't be as intelligible unless we customize the exact display of different elements. We can do this with some additional parameters in the plot method. If we don't customize anything, we'll get the weights of evidence by categories connected with a line, and that would be all. So, let's first make sure there is a marker for each weight of evidence by setting the marker parameter to lowercase o. This way, we tell the plot method to display a marker for each data point, and that the marker should be a dot. Next, let's keep the lines between the weights of evidence and make them dashed. The parameter for this is line style, and the value we need to pass to it is a string containing 2 dashes. Finally, let's make the color of the data black. Hence, parameter color equals lowercase k. Okay, this statement will give us the chart. Now let's put some titles on the axis and on the chart itself. PLT X label will put a title or a label on the x-axis. We want to see the name of the independent variable there. It will be different every time, but always the name of the first column of the data frame. So dfwo.columns0. Similarly, PLT Y label will put a title or a label on the y-axis. Here we'll always have weight of evidence, so we put the string weight of evidence. We can also put a title on the entire chart. PLT title will do just that. The chart displays weight of evidence by the independent variable, so let's put that as a title. We concatenate the string weight of evidence by space with the name of the independent variable and turn the whole thing into a string, so it can be displayed on the chart. Finally, let's make sure the labels of the x-axis categories are rotated equally as we discussed in the beginning. These labels are called x-ticks. We type PLT x-ticks, and in round brackets, we set the parameter rotation equal to our parameter rotation of x-axis labels. Again, don't worry about this part until we reach a problematic variable. All right, excellent. We wrote our function. Let's run the code. Great! Now, by calling plot by WOE on any data frame with results from weight of evidence calculations, we should get a visualization of weight of evidence by the categories of an independent variable. Let's try it out. We stored the weight of evidence calculations for the grade variable in a data frame called dftemp. Therefore, let's run the plot by WOE function on it. Awesome! We have successfully automated the visualization process too. In the next couple of lectures, we will focus on the interpretation of these graphs. Thanks for watching.